Next thing we're going to discuss are electron configurations, and essentially they're just a really convenient way to express a lot of the information we've discussed so far about electrons within an atom and ion. Let's discuss the three energy level or three quantum numbers that we're going to need to discuss electron configurations. Remember, energy levels, or N, they give information about the energy and size of the orbitals within an atom. A good thing to know here is that the number of electrons inside an energy level is equal to a very simple algorithm, and that is 2n squared. Okay, and this equals the number of electrons within that energy level. That'll be a really nice piece of information for us. So if n equals 1, 2n squared is 1, or 1 squared is 1 times 2. That can hold 2 electrons. N equals 2. 2 squared is 4 times 2 is 8. And then n equals 3. 3 squared is 9. 9 times 2 is 18. So it's going to be 18 electrons in n equals 3. Okay. Information about our sublevel. Remember, this is our L value, and those have letter designations S, P, D, and F, and those are the ones that we're going to use for electronic configurations. And then information about the orbitals is M sub L within a sublevel. Remember that the S orbital has one, or S sublevel has one orbital. P sublevel has 3 orbitals. D has 5. And F has 7, if you remember. Okay, one piece of information that we're going to use for the orbitals is the fact that 2 electrons can occupy 1 orbital. No more than 2. 1, of course, can be in there, but no more than 2. So if you think about the number of electrons in an s orbital, there's only one sublevel, one orbital, so there can be 2 electrons in s, 6 in the p orbitals, 10 in the d orbitals, and 14 in f orbitals. And we're going to use that information shortly. One of the things that we're going to quickly realize that even though electrons are within, say, a given energy level, it turns out that electrons within one energy level might not be the same energy, and this is going to give rise to the idea of degeneracy. And that comes from the fact that electrons outside, or on the outer edge of a atom, are actually shielded from the nuclear charge, or the positive charge contained in the nucleus. These electrons in the 1s orbital are flying around very high velocities. They actually block or shield some of the charge that this outer electron experiences. Okay, if that outer electron penetrates into the lower orbitals, say the 1s orbitals, it experiences a full positive 3 charge, the entire positive charge for this nucleus. And that stems from penetration. Now, we've said this previously, that the closer the electron is to the nucleus, the closer it is to that positive charge, the lower the energy of that electron. It lowers its potential energy because of the stabilization of the Coulombic charge attraction from the nucleus. So what this creates is a lowering of energy of different orbitals within a sublevel because of penetration. If we look at the radial probability distribution of the 2s orbital, remember that it has a node where there's a small region that has 0% probability of finding electron, and below that node there's some probability of finding electrons. What that does is these 2s electrons have a small probability of being very, very close to the nucleus, very, very close to the positive charge of the nucleus, which lowers their energy, which creates degeneracy, or the fact that 2p electrons and 2s electrons are different energy. And again, it's the interactions with the positive charge of the protons that stabilize the electrons, lower their energy. So if we look at that fact, the degeneracy caused by differing or penetrating nuclei, you can see a potential energy plot for all of the sublevels and their respective orbitals from 1s to all the way up to 4d here. Now here you can see that 2s and 2p orbitals are different energy because, again, 2s has that small area probability very close to the nucleus. 3s and 3p does the same. And it turns out that that this idea of penetration becomes so great than lowering the energy for some orbitals that it causes the 4s orbital to be lower energy than the 3d orbitals within a given atom. Okay, so even though the electrons in the 4s, n equals 4, have a higher energy level, n equals 4, they're actually lower energy than n equals 3, 3d orbitals because of that stabilization due to penetration. Okay, so when we describe the electron configuration for an atom, we are going to start at the bottom, start at the lowest energy, and work our way up, putting electrons into the lowest energy orbitals first, working our way up to higher energy orbitals. And this is known as the Aufbau principle, and this is German for build up. So when electrons go in an atom, they go from the bottom up, lowest energy to highest energy, and of course that is all due to stability. The lowest energy that they can occupy, the more stable they will be. Okay, so without looking at the plot, we're going to want to figure out a couple of ways to describe or figure out what orbitals are lower energy than other orbitals, and one way to do that will be pictured here. So what you're going to want to do is start by drawing a diagram that looks like this, with all of the sublevels in columns, S, P, D, F, and all the energy levels in rows, 1, 2, and so on. And what we're going to do is we are going to draw diagonal arrows looping back and forth, and this, in this fashion, will show us what orbitals are the lowest energy. So what we're going to do is we're going to start from 1s, we draw a diagonal arrow down, and we loop back up, and then come back down. So what that's telling us is we fill 1s first, then 2s, loop back up, and then 2p, 3s, loop back up, come back down, 3p, 4s, and there is our first indication that we're going to need to rearrange our energy levels. We apply electrons to the 4s orbital before the 3d orbital. And so that's the utility of this exercise, to show us the exact order in which we fill sublevels based on their energy. Then we're going to loop back up and come back down, and you can go so on and so forth. 3D, then 4P, then 5S, then keep going. And you can keep doing this, but as you'll see, it follows this plot of energy levels really well. Okay, so what we're going to do now is actually do an electron configuration. Again, this is going to show us information about the electron configurations within an atom. Okay, so what we're going to do is write it in this type of context. Okay, we draw the principal energy level first, as it's n equals 1, the letter designation of the sublevel, and then the number of electrons in the orbitals as a superscript next to the sublevel. So here would be 1s1, and that's how we would say that. And so that implies that there's one electron in the s orbital in n equals 1, and this could be neutral hydrogen atoms electron configuration, which has one electron. Of course, it's going to be occupied in the lowest energy level it possibly can, and then of course is 1s. More complex electron configurations like these, all we have to do is again look back to either this potential energy diagram or follow this schematic illustration for filling the orbitals according to the Aufbau principle. But essentially, you're going to follow this pattern and put electrons into the orbitals, or excuse me, orbitals and sublevels according to lowest energy to highest energy. So one of the first things I do is I try to figure out how many electrons each of these elements have, and if they're neutral atoms, we can just look at the periodic table, look at their atomic number. So titanium, Ti, has 22 electrons. So if you look back to either energy level diagram on the previous slides, you'll see that we're going to fill these up starting with 1s. We can put 2 electrons in the 1s orbital. Next energy level is 2s. 2 can go in there. So far we've applied 4 electrons. The next energy level is 2p. And we know that there's 3 orbitals in p. Each orbital can hold 2 electrons, so we can have 6 electrons in the 2p orbital. The next highest energy level is 3s, and that can only hold 2 again. Then 3p6, and then instead of going to that 3d orbital, we have to go to 4s2. And if we count those up so far, we've got 20 electrons, so there's 2 more electrons to display. And the next highest energy level is n equals 3, L equals 2, or D, and there are going to be 2 electrons in that orbital. Okay, so let's do selenium, which has 34 electrons. And so just like titanium, we're going to start at the bottom, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Now, because titanium only had 2 electrons, or 22 electrons, 2 electrons fit in the 3d orbitals. But selenium has enough electrons to completely fill that d orbital, and again, d sublevel has 5 orbitals, so it can hold 10 electrons. Okay, and then we have 4 additional electrons. So this would go into the next highest energy level, 4p4. Now, we specifically want to look at the next 2 elements, bromine, which has 35 electrons, and krypton, which has 36 electrons. And you'll notice that because we're going to fill the electrons in the same fashion from bottom to top, the electron configurations are going to be very, very similar, except for the electrons in the highest energy level. Okay, so bromine will look almost exactly the same. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And instead of only having 4 electrons in the 4p orbital, bromine has 5. Krypton has 1 additional electron than bromine, so the process will be the same. We're going to fill up from the bottom. That's a 3, 4s2, 3d10, and finally 4p6. Now, as you can see, each additional electron just went into the highest energy level. 4p6 is the ending for krypton, and the p orbitals can hold 6 electrons. If we're going to add additional electron for, say, the next element, which of course would be rubidium, we'd have to go to a higher energy level. And this fact that we can sort of build upon previous electron configurations in this manner, it turns out that there's going to be another way for us to figure out the energy levels of electrons just using the periodic table.